Good afternoon. So I will be presenting mostly a paper by Jun Yang and uh, Hyung Lee on neural network and answer set programming, or NeurASP. So the topic of this class is, of course, neuro symbolic reasoning, and the idea is to have frameworks where we can have both neural networks and symbolic AI. And this slides actually comes from Jun's slides. So neural networks can have raw data, big data, scalable. They can be robust, much robust, while symbolic AI has the positive of domain knowledge, and you can prove correctness and so on. So let me recap my view of various neurosymbolic approaches. So the first bullet is that is aimed towards people who come from purely machine learning background, that when you are learning, doing machine learning from data, you may have some knowledge and you don't want to learn from scratch all the time. So how do you incorporate that knowledge? And there are several ways of incorporating that knowledge. There is an approach called distillation. You can distill that knowledge during the input, and what it does is basically automatically creates additional data to train. If you have some knowledge, you may actually compile it into the loss function, and for a certain kind of knowledge that's now possible, and that's quite efficient. Or you could have a separate symbolic reasoning and filtering layer, and which is the approach that is used in this paper. So this is one group of neurosymbolic approaches. Another is, neural networks, and especially these days language models and Instruct GPT, they can generate code, and which can then get implemented by a program. So this is kind of another kind of a neurosymbolic integration. And you may have heard, like, say, big language models have trouble with doing simple addition, but they are pretty good at actually generating code that you can then, say, give it to a calculator. There are some recent papers in this direction. The third kind, I think, is the one which you have studied so far in the third and fourth. You have studied in the class. Neural models where each neuron has a symbolic meaning, and the overall network can learn various aspects from noisy data, maybe learn rules or capture logical contradiction, and so on. And another one is neurosymbolic approaches in the planning and acting domains, or in the reinforcement learning framework. So there, neurosymbolic architecture that learns state transitions from images is an example. So this is the paper that we are going to discuss here, the NeurASP by Jun, Adam, and Hyung Lee. So I'm going to present, and I have invited Jun to be around where I stumble, or if I have some doubts. He's the first author, and that's his PhD thesis, so he can help us more if we have any questions. So first, what are answer set programs? It's a logic programming paradigm where you have, so it's based on logic programming, or inspired by Prolog, you would say, where you have logical rules. But one of the key extension of this answers, or departure of with respect to logic programming, or the older style logic programming and Prolog, is that it allows these aggregates and choice rules where you can enumerate different choices. So let me show you some examples, and this comes from this paper. So here, the first rule is a choice rule. The ones in the red are choice rules, and they're basically saying that the first one says in each answer set, the digit of D1 should have one of these values between 0 and 9. And the second choice rule says in each answer set, there should be the digit of D2 should have value between 0 and 9. So in essence, you would have, just by these two, you would have 81 different answer sets. And in each answer set, the digit D1 will have a value between 0 to 9. and D2 will have a value between 0 to 9, and you will have all possible combinations. So the choice rules allow you to do that. And then the next one is kind of prologue kind of rule. It says the addition of A and B is N if the digit in A is N1 and the digit in B is N2, and N is the sum of N1 plus N2. And so this arrow is the if. So the third, this is a typical kind of prologue kind of rule. It's a logic programming rule. And in answer set programming, you are allowed to have these choice rules. And what this does is it allows you to express NP-complete problems. You can enumerate the various possibilities and pick the right ones. So, and the answer set or stable model, this is one stable model here. I said there will be 81 different stable models. And say one particular one would be digit D1 has value 3, digit D2 has value 0, and addition of D1, D2 is 3. So let me give you some more example. Another example, this I picked up from the Wikipedia. So suppose you are doing graph coloring. So the answer set program for graph coloring would be, you will have facts saying, suppose you have the vertices 1 to 100, and then you have a set of edges saying there's an edge from 1 to 55. So that's how you describe the graph. And now you want to color them. So depend on what kind of coloring. So we know that 3 coloring is NP complete. Is 3 coloring? I forget. So suppose you have n number of colors. So you can say color 1 to n. So now this one is the choice rule saying for each vertex X, it can have exactly 1 color. So this is the notation of saying for each vertex X, the set of color X1 such that Ci is a color ranges from this set has only 1 element. So the size of this set is between 1 to 1. That means exactly 1 element. So what does it do is for each vertex, it assigns a color. And now colorability, graph coloring is the point is that we don't want 2 adjacent nodes in the graph to have the same color. And that is expressed by this rule, which has an empty head. So it's considered as a constraint saying if color of X is I, color of Y is I, and there is an edge from X to Y, then that's not good. I mean, the empty head means that it's inconsistent. You should throw away any answer set which has this condition true. And just these 3 lines and this description of the edges and the vertices is enough. I mean, if you give this to a answer set solver, then it will generate. I mean, you can ask it for generate 1 answer set or all answer sets, and each answer set will give you a coloring. If there are no answer set, that means there is no way you can color this graph with n colors using this many number of using n colors, satisfying this constraint. So that, I think, a quick glimpse of stable models or answer set programs. So let's talk about, so what is NeurASP and why we are doing it. And as we will show that NeurASP is neural networks for answer set programs. And as June has written, but why? It has several positive aspects. First, as you will see later, it allows one to train a neural network under weak supervision. That means less data or data that you can create automatically fairly easily. And here, the examples, next example, see, you can nicely separate the perception part and the reasoning part. And moreover, the reasoning part can help make the perception model, which is the neural network model, the perception part better or more robust, more robust. The fourth one is more elaboration tolerant on visual tasks. This is a term in the sense we were talking about, say, graph colorability. If we want to change our task a little bit, it's very easy to do that because we can write or modify our rules. And so the final one is, it says, final bullet A neural network can be trained together with rules so that it not only learns from implicit correlations from the data, but also learns from explicit complex semantic constraint expressed by ASP rules. So you have additional knowledge that you can use in learning. And as you will see in the experiments, this leads to being able to learn from less data. So how does this work? So let's take the key example in this paper. So here we have two handwritten digits, D1 and D2. And the data set is basically, is input is two handwritten digits, and the output is the sum. And the goal is how. So the goal is that we want the system to learn how to recognize as well as to and output the sum. So here is how it goes. So there is D1 and D2. There is handwritten. These are handwritten digits, and there's a neural network, maybe convolutional neural network. And this network, what it produces is 20 probabilities. Actually, yeah, 100. So 20. I was saying 9 into 981. Sorry, 100. So here, so 20 probabilities. The probability of this one P10 to P19 is basically saying that this digit P10 means what is the probability that this digit has value 0 or is 0. What is the probability this digit has this digit is a 1. So these are the 10 probabilities that this digit is between is 0 or 1 or 2 or up to 9. Similarly, there's a probability if this digit is 0 or 1 or 2 or up to 9. So the neural network is, they would give you that probability. That, I think, if you know neural networks, you understand how this happens. You have the neural network, and you can have a softmax layer, and the softmax would generate you these probabilities and these probabilities. And okay. Or you can have just separate probabilities. You don't necessarily make to add them up to 1. Now this is the ASP part. So the ASP part, I already showed you the same one. It says that digit D1 has value 0 up to digit D1 up to 9, and says that you should have answer sets. So I'm not sure if June might clarify, is the one missing here? Otherwise, it would generate some answer sets without any digits.
This is the syntax in Klingo that we can use equals to 1 to express 1 on the left and 1 on the right.
Oh, okay, right. Oh, I didn't see equal. Yeah. So it's basically saying that in each answer set, this should be exactly, you should pick exactly one of it, one of these. And similarly, yeah, here you pick exactly one. So this is the Klingo syntax of it. Okay. So now, I mean, so this is the neural network. This is this, and this is the addition. And so now you have this, and so this is your whole network, or this from here to here, if I should use this thing, is your whole system or a model that you normally we call this neural network model, but now this is a NeurASP model. So like in any ASP training or any training, what you will do is you'll give input and you'll give in the training phase output. Say in this case, you give output 3. And the system would then not only would learn, I mean, there's nothing to learn here, so it will learn all the parameters here. But of course, to learn and to do back propagation, we need to define back propagation over this, over the ASP part. I mean, we know how to do that, or it's well known, the back propagation over the neural network path, but you have to define the back propagation over the ASP part. So, okay, so we use neural network digit. So this is this one to classify the image D1, and the output P1I for I in 0 to 9 defines the probability that digit DI, like D1 or D2, is has the value I. So now to going to a little more formal definition. So this leads to a neural atom called neural network, digit 1 D1 0 to 9. And similarly, there will be another, right? Neural network digit 1 D2 0 to 9. Yes. Okay. And this one, it basically, as I understood, I had to figure that out, is that for each D1, you can have multiple ways of looking at it. And here we are just thinking of only one probability. Like in another example, when we do Sudoku, you will see there will be like many more. In case instead of one, there will be much more. Here, for each digit, there's only one thing we are worried about, one probability that we are, one set of probabilities that we're worried about. Right? Okay. So the syntax of a NeurASP. So this is a traditional style of writing papers in knowledge representation and in theoretical domains, that you define the line syntax of your language. So the syntax of is a NeurASP, a neural network is represented by a neural atom of this kind. So this is what this is formalized. So there's a neural network. Then there's M is an identifier. So here M was digit, and then E and T. So E is this one. I just said there's only one here, but that could be more in another example. And then D1, that's the T. And then you can take values between V1 to Vn. So it's here 0 to 9. So this is a neural atom. And in this code, there will be two neural atoms. There will be this one, NN digital 1 D1, and there will be another NN digital digit 1 D2 with the same thing. So NN is a reserved keyword. M is an identifier of the neural network. T is a list of terms that serves as a pointer to input tensor. V1 to Vn represent all n possible outcomes. And this one is of the E random events. This will not be clear now, this E, but just remember, in this case, E is just one because there's a one way we are looking at this particular digits. But in some other examples, we could have more number of ways to looking at an image. A NeurASP program consists of neural atoms, basically the network, and ASP rules, or answer set programming rules, which are this example. So it's a formal definition of what is a NeurASP program. It is this part and this part. And this part is formally defined using such neural atoms. So inference. So once we have a neural networks, so how do we infer from it? So now we are not talking about learning, we're talking about inference, right? So inference, you are given input, there is no output. I mean, the output will be obtained. So you are given input. So let's really actually calculate. So you're given input. So what happens is this network is going to give you these probabilities, right? And so what happens, let me write it down here. So you will have 100 different, okay. So you will have 100 different answer sets. So in one answer set, you will have, say, I'll just say D, instead of writing digit, I'll just say D, digit of D1 equal to 0, and digit of D2 equal to equal to 0, and digit of D2 equal to 0. Okay, and you'll have other things. Let's just ignore other things. Will be basically the addition part. Addition of this will be 0. It will be there. So this is one answer set, and there will be 100 such answer sets. Digit of D1 equal to 9, and digit of the final one D2 equal to 9. Okay, so now each of these is, there's a simple way to look at it. We can assign probabilities to each of these answer sets. And how? That we know that this probability is probability of 1, 0. So this probability of this answer set is probability of 1, 0 times probability of 2, 0. While this one is probability of 1, 9 times probability of 2, 9. Okay, so we have 100 answer sets, 100 such answer sets, 100 such answer sets. Okay, and you have 100 such answer sets with this probability. And suppose I ask a question, okay, is addition of this digit is, I ask the question, I'll ask the question, ask the question, say, is addition of D1, D2 is 15. Okay. So the answer would be, or what the outcome will be, the outcome will be a probability. You'll say yes with probability this much. Outcome will be a probability. Would be a probability. And what is that probability? That probability will be, you look at all these 100 answer sets, and wherever the addition is 15, you add up all those probabilities, and then you can divide by the sum of this if you want to get to normalize it, to make it really probability. In the simple implementation that they have, that's not important, so they don't normalize. But theoretically, you can define the probability of this addition D1, D2, like these two things that you saw. The addition of this is 15. Is you look at, okay, what is the value? This is 0, 0. Of course, this is not 15. So whenever this you see 15, and whatever the corresponding probability, you add all of those answer sets, add all of them, and that's the outcome. That will be the probability associated with this. And I think that's what is described here. Yeah, is the way I put the multiplication, and for addition of D1, D2, 3. So for 3, it is 0 and 3, 1 and 2, 2 and 1, and 3 and 0. So it's the probability of this model, this one, this one, this one, and you sum it up. Okay. So that's the inference. And I think we don't need to discuss this. Semantics is basically simple, that you have, I mean, I already told you here, you collect all these all the answer sets. So similarly, the semantics of NeurASP is formally defined, that you create all the answer sets and assign the probability, and that's the semantics. Learning, and this I explained, but we can go over more, a little more. So the learning is, in the learning phase, you are given this input, and you are given a possible label or output. So now you have these probabilities. I mean, you have this neural network, and this neural network will calculate probabilities, and you have this, and you have this. So the way to learn it is, of course, when you see and if it doesn't match, then you have to do back propagation. So somehow you have to define this delta of these probabilities, and with respect to theta, all your parameters here, and that is by chain rule, is a summation of delta of this up to, with respect to this probability, this layer, and then the delta of this to this. And this is normally known, means this you discuss in the neural network classes. And in this paper, a key contribution is defining this. How do we define the differential or the partial derivative of this with respect to this?